Okay, for this section, we're going to look at the multiplication and division of integers. So we've already done addition and subtraction. So if you remember that, multiplication is really just repeated addition. And so it's going to behave similar to that. And division is just repeated subtraction. So we're going to use some of what we learned with our adding and subtracting of the integers here. So before we go on to that, there's a few properties of multiplication, and these are all words or vocabulary that you have already seen before. So the first one, closure property. So multiplication has the property of closure, and that is that if you have two numbers, a and b, that are in I, that is, they are the integers, then the product, AB, is also an integer. The commutative property, we have that for addition. We also have for multiplication. So remember, you can commute, change the order. The associative property moves around the parentheses. So instead of doing AB first, you could do BC, multiply those, and then multiply by A. The identity property says that if you have A and multiply it by 1, you would still have A. And the distributive property, we've been using that a few times already. That would become AB plus AC, and it also works for subtraction. So a little side note that if you have A times B minus C, that's also going to be able to distribute as well. And then we have the zero property, which if you multiply by 0, we've already seen this with whole numbers, you're going to end up getting 0. So we're going to look at the chip model of multiplication. And so when we have this example here, 3 times negative 5, we can just say that this is making 3 sets or 3 groups of negative 5. Negative 5, we can represent it as like little minuses if you want, or it's already drawn for us, these little red chips. And so if you have 3 groups of 5, then all together we're going to have negative 15, because there's going to be 15 negatives now. So if we look at the next problem here to try, so you could pause it and then try these ones, but I'd like you to use the chips to show what the answers are. So 5 times negative 2 means 5 sets of negative 2. So we're going to have a negative 2, negative 2, negative 2, negative 2, negative 2. So all together here, we're going to have 10 negatives. Now, negative 2 times 5, since we can commute these things, we can rewrite this as 5 times negative 2, and then we still have that it will be a negative 10. Now, negative 5 times 2, this one, if we commute them, it's 2 times negative 5, so we could say 2 groups of negative 5, and that's still going to be a negative 10 as well. For the bottom part here, we have 3 sets of negative 8. So 3 sets of negative 8, you can already know without memorizing, oh, negative times a positive is negative. We can just think about what that means. We'd have 3 sets of negative 8, which would be 3 times 24, but they're all negatives. 6 times negative 9, kind of same thing. So you're going to have 6 sets of these 9 negatives. And so we can quickly say, oh, well, that's going to be 6 times 9, but we got to keep in mind that they are all negative. So we're going to have negative 54. And then similarly here, we could rewrite this as 5 times, oops, not 5 times negative 8. We could rewrite that as 8 sets of negative 5. So 1, 2, 3, 4, 5. We're going to do this 8 times. But as you do that, you're just going to end up with 8 times 5 and just knowing that they are negative. I think I didn't count these right, but that's okay. So we have 1, 2, 3, 4, 5, 6, 7, 8 rows. So that's going to be 40, but they're all negatives. So when we have something a little bit different, like a negative 3 and a negative 5, we can't use the commutative property, and it doesn't really make sense to have 3 groups of negative 3 groups. Like, what does that mean? And so the way that we see that with these chips is that we're going to remove 3 sets of 5 red chips. So if we want to take away 3 sets of 5 red chips, well, we already know that we want to take away from the previous problems 15 red chips then. And so in order to take those away, we have like nothing to begin with. So we can make these 0 pairs. So this was where we had a white and a red, but that's really like that plus and the minus where together that's a 0. So if you look at what we have, this whole entire quantity here is really just 0. And so if we want to now take away 3 sets of 5 red chips, this is the take away, take away, take away, all that's left is 15 positive chips. And so we can say that -3 times times -5 is going to equal positive 15. So there's going to be a couple of different models. So maybe you don't like that one so much. Maybe you think, oh, that makes so much sense. So we're going to see a few different sets of that. We're going to cruise to the next page, which has the answer of that 15. So we can try a few more of these. So again, you're looking at -4. That's taking away 4 sets of -3. Taking away 4 sets of -3. So we know that we need to have -3. We need to have 4 of those. And so we're going to make those 0 pairs. And so when we try and take away these 4 sets, these are going away, going away, going away, gone, 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 gone. All we're left with is positive 12. So similar here, we're going to take away 5 sets of -4. So in order to take away 5 sets of -4, we need to have them. And we're going to make those 0 pairs. And that way when we take away those 5 sets of 4 negatives, all that's going to be left is that positive, and there's going to be 20 of them. And so if we think about that happening again, we're going to have taking away 2 sets of 6 negatives. Well, we're going to still be left with 12 positives. So what do they all have in common? They're all positive because we're taking away that negativity. Next, we're going to take a look at the number line model, which we saw before with our addition and subtraction with our negatives. So we're going to look at trying to multiply 2 times -3. So that's going to be our first start. So we always start at 0, and we're facing to the right towards all the positive stuff. And so if we're going to look at 2 sets of -3, well, really, that's going to go backwards because that negative means backwards 3. And we're going to do that twice, 2 times. So what that would look like is you're going to go walk backwards 1, 2, 3, but you're going to have to do that one more time. So you do that in different colors. So 1, 2, 3. And so then all together, you are now here at -6, and you're still facing that way. So then what about if we have like -2 times -3, like what could that mean? It needs a little bit of a different interpretation. And so one way that we see this negative in the front is that it could be the opposite. And so on a number line, remember opposite meant the other side of 0. So if the first part is going to be 2 sets of -3, we could show that again. So we're at 0. We're going to do 2 sets of -3. So we're going to go 1, 2, 3, just like we did a second ago. And then 1, 2, 3. So we're still facing backwards. We're at -6, but now it's saying, well, let's take the opposite of that. So that would put us on the other side here at +6. So this is going to be 6 now. So the other model for multiplication kind of looks at patterns. So we already know, looking at 3 sets of -2, that's going to be -6. And we know 2 sets of -2 is going to be -4. 1 set of -2 will just be -2. And so kind of looking at just the pattern, each of these is really plussing 2 each time. So we know 0 sets of -2 is just going to be 0, and that's also our identity, or not our identity, but the 0 property. But you can see it's still following that pattern, plus 2. Now, -1 times -2, if we're not so sure about what that negative is going to do, just think about, we're going to follow that pattern of plussing 2, then we're going to have a 2 there. And we plus 2 again, following that pattern, we're at 4. Plus 2 again, and we're at 6. I don't even know what the problem is here. That would be -3 times -2, which is what you would expect. So then what we get out of this is a definition for integer multiplication. So as long as we have that a and b are integers, then what we're going to say is if a is greater than or equal to 0 and b is greater than or equal to 0. So basically you have 2 positive integers, which really means whole numbers, then their product is just a times b, just like we're used to. Now when we're looking at one number being less than or equal to 0, actually both of them, then their product is going to be the absolute value of each of those guys, which ends up being a positive number as well. This is going to be positive AB. Now, if one of A and B is less than 0 and the other is greater than 0, so basically one negative number and then one positive number, then we're going to end up with a negative, because this part right here is going to be our product of just the numbers, kind of ignoring the signs, and then we need to make that answer negative. So for example, if we're looking at -3 times +2, we've already said that that's going to be 2 sets of -3, so we can say 2 times 3, which is 6, but then they're all negatives. Now we're going to take a look at integer division, which we've already talked about division, and we're going to just look at it a little bit more with the integers. And we're going to really depend on the definition that when you're dividing two numbers, that division is equal to the unique number c, that if we take b times c, we'll get back to a. So what that looks like is if you're taking something like 6 divided by 3, which we already know equals 2, this statement here says that 6 is equal to 2 times 3. So that's really like the check that you would normally do. If you want to check that 6 divided by 3 is really 2, really you're saying, oh, well, 2 times 3 equals the 6. Like that's your check. Now, following that, we've already mentioned before, but just to kind of reiterate it, that if b is 0, it's undefined. That is if you take an a and divide by a number 0, there is no number here that will be able to be multiplied times 0 to make a. So sometimes people say, oh, well, I think a divided by 0 is equal to 0. But no, that can't work. Because if I'm going to check it, that means that this 0 that you guys just said, the answer, that's like the c up above, would have to multiply times 0, which is like the b up above, and make that. But 0 times 0 is equal to 0. So it's not going to work for us. So we will always say that a number divided by 0 is undefined. And that can be written a few different ways. Sometimes we'll write it like a over 0 or a divided by 0. All of these are undefined. So we kind of defined integer division in terms of multiplication, but we can still use the chips or kind of play around with the chips a little bit. Your book doesn't really go through this, but I thought it would be nice to see how the division would work, because we've talked about dividing two integers or dividing two things and how that's just splitting up into equal groups. And so whenever we are dividing by something, a reminder that that's called the divisor. And when the divisor is positive, we can think about it in terms of sharing. So the divisor tells you how many groups to make. So let's kind of scroll to the next part. So looking at this next page, if we see negative 12 divided by 3, right, that's our positive number, it's telling us that's how many groups we're going to have, or how many sets we'll have. So here's group number 1, group number 2, group number 3. So we're taking the negative 12 and splitting it. So it's like you get 1, 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 until you use them all up. And so when you do that, those 3 groups are each going to have 4 red chips in them. So then we're going to say, well, negative 12 split up into 3 groups will be equal to the negative 4. And of course, we can check it using that definition, and that check is that negative 4 times the 3 equals 12. So if we have negative 15 divided by 5, that's going to take our 15 negatives, so we'll have 15 negatives kind of hanging out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's taking those 15 negatives and it wants to take them into 5 groups. So we need a group 1, 2, 3, 4, 5. So some people like to split it evenly like I kind of showed you up above, but we can also try and split it like we kind of know that we can take 3 at a time, because we already know what 15 divided by 5 is. So now it's just saying that they're negatives. So each of these groups is going to have 3 negatives in it. So negative 15 divided by 5 we'll say is negative 3. So following that, again, you can see we have negative 14, that's 14 negatives, divide by 2. You can draw the picture, but you know that you're going to have 7 negatives in each group. Negative 18 divided by 3 groups, that's going to have 6 negatives in each group. And negative 26 divided into 2 groups gets you negative 13 in each. And all of them you can check by multiplying. Negative 7 times 2 does equal negative 14 from our previous page. Negative 6 times 3 equals negative 18. And negative 13 times 2 equals negative 26. Now, both numbers are negative. It doesn't totally make sense to like share into negative groups. So instead of thinking about that, we can do it in terms of measuring. And so what that means is the divisor is going to tell us what to put in each group. So if we're going to take negative 16 divided by negative 8, it's saying that we want to have negative 8 in a group. And so the question changed a little bit to be how many groups there could be. So if there is 1, 2, 3, 4, 5, 6, 7, 8 here, 1, 2, 3, 4, 5, 6, 7, 8, there is going to be 2 total groups. So then we say that negative 16 divided by negative 8 is going to be positive 2 for 2 groups. And it continues on to check that 2 times negative 8 equals 16. So again, we can try this a little bit. You can use your red and white kind of chip idea, but we have 16 negatives and we want to put negative 2 in each group. That would make 8 groups. Negative 18, we have 18 of those negatives and we need negative 9 in a group. That would make 2 groups. 25 negatives and we want 5 negatives in a group. That's 5 groups. So you can see that all of our numbers are coming out to be positive because that's the total number of groups you can make, which can't be a negative amount. So 160 negatives divided into 4 groups, that's going to be 40 groups. 48 negatives divided, where you have negative 8 in a group, leaves you with 6 groups. 48 divided by negative 6, well, that's negative 7 in a group, so this time you'll form 8 groups. And all of these you can double check by doing your multiplication. So the last thing we're going to look at is ordering our integers, and we're going to look at the definition of less than for integers. So if you have a and b are integers, we write a less than b, but that's only if there's some number k that when you take a plus that k, it could be b. So in other words, if A is littler than B, if you subtract them, so again, this is the bigger guy, this is the little guy. If you subtract them, you get a positive number K. K is positive. And so it's what you would expect, but it's just kind of a more formal way of defining it. And so we want to look at Theorem 511 from your book, and it has some different operations kind of that they do with inequalities. And so if you look at part A, it tells us that we have the situation x is less than y. It says if that's happening, then we know that x plus n will be less than y plus n. So one of the questions that you want to ask is, well, why does that work out to be true? You can look at an example, so that's always a good start. Use some inductive reasoning to try and see if that's going to be true. So let's look at 3 is less than 5. That's a true statement. And so if this is true, what part A says is, well, if I add the same number to both sides, let's add 6. So is that still a true statement? Well, yeah, this is 9 and that's 11. It's still true. So just by example, it seems like it's meeting that. So if we go back to the definition of less than, we have to be able to meet this requirement about some positive number when you take the difference of them. So the justification for part A is that if x is less than y, then we know that, so if we have that x is less than y, then we know that y minus x, so the big guy minus little guy, is positive. It's bigger than 0. What we want to show is that in order for x plus n to be less than y plus n, then this would mean that y plus n minus x plus n, so this is again the big guy minus the little guy, would have to be bigger than 0. Well, this is just y plus n minus, we can distribute the negative. So we're going to get negative x minus n. But we already know that, well, n minus n, that will cancel. So all we have left is y minus x. Well, that is greater than 0. That was given to us in the beginning. So that shows that the inequality x plus n is less than y plus n is true. And so the other parts take a similar justification. So we can let's try one more. So that was part A justified. Let's look at part C. So part C says that if we have that same x is less than y, but this time we have n is positive, we want to show that nx must be less than ny. So again, if we have this first part, we know that y minus x is greater than 0. We also know that n is greater than 0. So let's see, if this last part is going to be true, we want to show then that ny, that's the big guy, minus the little guy, is going to be less than 0. Well, this is just n times y minus x. And we already know that y minus x is bigger than 0. That's what that statement already says. And we know that this is greater than 0. So that means we have a positive number n, and we have a positive number here, and we've already learned that if you have two positive numbers being multiplied, that will be positive. So then we know that ny minus nx will be less than 0. And that shows that nx is less than ny. And you can do this again similar for part B and C.